this class and share it so you can see the examples being done. And we're going to talk about the Navier-Stokes equation, which we talked about in kind of a general way last time. So if you'll remember, the continuity equation, which we talked about last time, was a differential mass balance. So what kind of balance is the Navier-Stokes equation?
Momentum.
Momentum, yes. And as a review, what you have here is sort of a momentum change, which we set equal to a force balance, just like when we did the macroscopic integral momentum balances. And you get your pressure forces, your gravitational forces, and your viscous forces over here on this side, and your momentum change on the other side. And today we are going to, in fact, one of the first things y'all asked me when I presented you with this equation was, what's the point? What could we use it for? So we're going to do 2 different examples today, using it to solve problems and figure things out. Now, a review of coordinate systems, because we're going to use 2 different coordinate systems today and in general. There's Cartesian coordinate systems, which we're familiar with, your X, your Y, your Z. A lot of times people use this one as the Z and this one as the Y. It doesn't really matter though. And your cylindrical coordinates, which we're going to use a lot. So just remember that in cylindrical coordinates, you have R going out like this and also like this. So the radius. You have theta, which is the angle like this, and then you have Z, which is going like along the cylinder. Cool. And we can break the Navier-Stokes equation into Cartesian coordinates like so, or into, that is wrong right there, I will fix that, or into cylindrical coordinates. This is what I was referring to. This should be d squared w dy squared. Anyway, or cylindrical coordinates, and it looks like this. And today we're going to do one example problem with Cartesian coordinates and one with cylindrical. And in both cases, the basic general approach is you write out your Navier-Stokes, you simplify it, and then you integrate. As it turns out, as you can tell, since this is a pretty complicated equation, it's exact solutions are only possible, like exact solutions that we can figure out by integrating by hand in a handful of situations. I said last time that most of life, the most common use of Navier-Stokes is approximate solutions, usually done by a computer to do CFD. But we are going to be looking at some of the situations when you can get exact solutions. Okay, first one. I give you a velocity field right here. This field is steady, it's incompressible, it is 2D in the horizontal plane. A, B, and C are constants, and we want to find pressure as a function of X and Y. So we have pressure, we have velocity. Navier-Stokes relates pressure and velocity. And so the first thing we do is we write out the Navier-Stokes equation and we simplify. So let's go through everything we were told about this field, figure out how to simplify this. First thing, it's steady. So if it's steady, what can we cancel out of these equations?
The time derivatives?
All the time derivatives. Cool. All right, it is incompressible, which mostly just means that the rows here can be considered constants, but you can't cancel them out at this point. Okay, it is 2D. What are the 2 dimensions that it is?
Would it be X and Z?
So first of all, if you look at the equation, it uses X and Y. And then I tell you to find pressure as a function of X and Y. So clearly we're doing an XY plane like this, where this is X this is y, and this is z. Which letter you put with which direction is kind of arbitrary. So we look here, it has x and y in it. It says it's horizontal, so it's a plane like that. But that means there's no z. So what can we cancel out now?
W.
W. Anything with w. So the whole z component of the equation goes away. Okay. And then everything else with w in it goes away. And everything else with z in it goes away. So the fact that it's a horizontal plane also means that gravity is acting in this direction, and we can assume gravity isn't acting in the horizontal direction. So what goes away then?
Your gravity term in the second line.
In both of them. Yeah, gravity isn't acting in the x direction, but it also, or the y direction. We can assume gravity is acting vertically, so it's not acting in either the x or y direction. They both go away. Cool.
Then when would gravity ever be there in the x and y direction?
So sometimes that g term is not gravity per se. Like, what if you were on a spaceship and it was accelerating that way, or a train? Let's say you're on a train and it's accelerating that direction. So there is a force acting like gravity going that way. That isn't technically gravity.
Could you explain one more time just why we can cancel them in this case?
Okay, so gravity acts in the vertical direction, which we have defined as z, because this is 2D in the horizontal plane and it's x and y. So that what
Okay,
that
gotcha.
means is that we have defined this as x, this is y. There's no gravity acting in those situations. As I said, there could be, if you could have a situation where there was gravity or something like gravity acting that way, electromagnetic forces, something like that, but there's not here. And so, therefore, okay. And so let's look at this. That should be everything. Okay, so now that we have simplified out, I'm going to write out the simplified version like so. And I just went ahead and solved for P on one side because I knew we were going to want pressure eventually. Okay. Alrighty then. So let's now plug in things here. So I'm going to write, going back, let's see, u, so the x, so u is the x velocity. So what does u equal here?
AX plus B.
Ax plus b. And v is the y velocity here. So what does v equal?
The other one.
The other one. Negative ay plus bx, I think. Let me look. Cx. No, go back. Okay. Plus cx. Beautiful. Okay. Negative ay plus cx. And so looking through this, we're going to want du dx. What's du dx?
X.
A.
A. Du dx is a. What is du?
Negative A.
No, du dy.
Oh, is that 0?
Zero. Thank you, Valerie. Okay. I'm trying to remember to do the little swirly d's so that we'll all remember these are partial derivatives. Okay, dv dx then is equal to
C.
c, and dv dy is equal to,
Now it's negative A.
now it's negative a. Yep. Okay, and looking into that here, let's see, we get, okay, great. And now we need to do a second derivative for these guys. So what is d squared, or the second derivative of d of u with respect to x, this guy? What's
Wouldn't
that?
they all be 0?
Yep, they'll all be 0.
Question. I know in this case they're all 0, so it doesn't matter. But should it be a positive term in front of the mu, or is it negative?
It is negative because what I did is I solved for dp dx, and this is negative, so I put it over on that side. Oh, I see what you mean. Let me double check to make sure I didn't put in a typo. Okay, it should be a positive. So that was a typo on my part. Thank you very much. But in this case, it all comes to 0. Okay, and we end up with, kind of put dp dx is equal to negative rho times ax plus b times du dx, which is a, plus negative ay plus cx times 0, like so. Negative rho times a squared x plus ab. Okay, and then dp dy is equal to negative rho times, let's see, ax plus b times dv dx, which we said was c, plus negative ay plus cx times dv dy, which is negative a, which I'm going to simplify down into negative rho times acx plus bc plus a squared y minus acx which allows us to cancel out acx, which is nice, and we get negative rho times bc minus ac. I'm going to call that b minus a. Oh no, never mind. Oversimplifying. Times a squared y minus ac plus bc. Okay.
Where are you getting that AC from?
That ac, oh no, never mind, that canceled out. That was the acx that I literally just canceled out. Instead, it is just this. There you go. All right, so now we have an x differential equation and a y differential equation, and we can solve these. Let's start with the x one. Yes. let's see. So let's start with the x one, which is, let me see. Here we go. dp dx is equal to negative rho a squared x plus ab dp is equal to negative rho a squared x plus ab dx. Boom. Boom. All right, someone want to solve this for me?
Density isn't changing, so we can move that out, right?
Yep, it isn't changing. It's just a constant. You can move it out.
Is this going to be a definite or a indefinite integral?
It will be an indefinite integral, but remember this is a multivariable equation, differential
So the
equation we're
constant-
solving. So the
the
constant
constant
will
of
be
energy.
a function of y.
So is it negative rho a squared times 1/2 x squared plus abx plus fy?
Mhm. Yep. Yes, it is. Plus f of y. Okay.
That x squared.
Yep, that x is squared. So that's great. And then we also have dp dy is equal to something negative rho a squared y plus bc. Wait, yes?
Can you remind us why we have to add f of y?
Okay, so this pressure is a multivariable function. It depends on both x and y.
Okay.
Okay? And when you take pressure and you take the derivative with respect to x, dp dx, the partial derivative right here, y acts like a constant and it something that just had y and it would just go away, right?
Mm-hmm.
Great. So
Also, for the integral, oh, sorry, were you still explaining that one? Or-
yeah, let me just finish saying that.
Okay.
So it's a partial derivative. So if you would take p and you take the partial derivative with respect to x, anything that just had y in it would act like a constant and it would go away. And so then when you're doing it backwards and integrating, you end up with the constant, which is just everything that would go away when you take the derivative, right? So everything that you don't know what it is, and that could have y in it.
So when we take the derivative of dp dy, is that like the plus fy function?
Yes, it is. Well, we're gonna do that right now. We're gonna do the y part and we'll see how we put them together. Someone else had a question.
Savannah.
Savannah.
Never mind, I'm good now.
Okay. It was negative a squared x plus bc. Okay. Plus bc times dy, and the integral is pretty similar to the one we just did, so it's just p negative rho 1/2. Actually, wait a second. That should be y. There we go. 1/2 a squared y plus bcy plus f of x. See? So we did the same thing with both of them. And when we did the integral with respect to x, you end up with f of y as your constant. And when you do the integral with respect to p, you end up with f of x as your constant. And if we look at these, you will see that what the f of y right here, it's got to be this. And the f of x right here has got to be that. Or you could just set them equal. That's probably the clearest way. Like you could say negative rho 1/2 a squared x squared plus abx plus f of y is equal to negative rho 1/2 a squared y plus bcy plus f of x. And when you do this, you should see that these sides are equal. We know they're equal because because they both equal p. And so therefore, this must be what that f of y is, and this must be what that f of x is. And you end up with a final answer, which I'll put right here somewhat sloppily. P is equal to negative rho times 1/2 a squared x squared plus abx minus rho times 1/2 a squared y plus bcy. Or you could, if you wanted, it could be
Dr.
like,
Nickerson,
yeah?
the y next to the a squared is supposed to be squared as well.
There you go. Thank you. Yeah, and then you could simplify it down from there. Like you could say negative rho over 2a squared times x squared plus y squared plus minus rho a bx minus rho bcy. All of those would work. Point is, we now have pressure as a function of x and y.
Dr. Nickerson, would
Yes?
this be a Eulerian way to look at it because it's about a certain fixed point?
So this is, it is a Eulerian way to look at it because if you'll recall, the Eulerian way to look at it is you get just a field. So anytime you find pressure as a function of x and y, so you could plot this. You could plot x and y and you could have some kind of color for pressure, and that would be the pressure field. That is a Eulerian way of looking at it. Yeah. Okay, but so it's not looking at a certain fixed point per se, but you could pick any x and y and you can figure out what the pressure is there. And you can do that because you know what the velocity function is there, and you have the Navier-Stokes equation, so that's nice. All right. Any thoughts about this? So again, we did some multivariable integrals when we were talking about the continuity equation, but for those ones, we weren't able to figure out what f of y or f of x was because we didn't have enough information. This time, we had enough information to do that, so that was nice. All right, so now we're going to find the velocity profile in a pipe. We have talked about flow in a round pipe before, and I would just give you the velocity profile. And we did a few different kinds of problems that used the velocity profile to find someone else. Does anyone remember what sort of thing we could use? So the velocity profile, so that would be like V of R. So we have a pipe like this, and there's a radius here, and we find V of R, which usually looks something like that for laminar flow in a round pipe. What sort of thing could we use that velocity profile for?
Isn't that how we can find out what alpha is?
Yeah, that's how we could find out what alpha is, the kinetic energy correction factor. Also the momentum flux correction factor from last time. You can use it to find shear stress, right? That's an important one. So when we were doing non-Newtonian fluids, we found the velocity profile and used that to get all of those equations for pressure drop and Reynolds number and all of that. Those all came just from the velocity profile. Okay. Alrighty then. So we have a round pipe. The flow in it is steady, it is laminar, it is incompressible, it is Newtonian. It is long and it is constant. The pipe is long and it has a constant diameter. I'm going to talk about what all of that means. So the point that it's long, the reason that's important is because it means it's fully developed. Does anyone remember what fully developed means?
Doesn't it mean that the velocity profile won't be changing along the pipe after a certain point?
Yes, that is what it means. It means like right when you get into the pipe, the velocity profile is kind of changing as it goes along, but it gets fully developed and then it's just the same for the rest of the time and it's constant. Cool. So it is round, it is constant diameter. There is a name for this specific type of flow. It is called Poiseuille flow, which I am not 100% on that pronunciation because I mostly in my life have just seen it written, but I think that is it. It's French. Anyway, so Poiseuille flow. And we are going to find the velocity profile for Poiseuille flow, E sub r. And we're going to do the same thing that we just did. We are going to simplify. And in fact, because this is kind of a complicated one, and I really want you to know about how to simplify the Navier-Stokes, because that's half the battle, is the simplification. We're going to do this here. So first of all, it's steady. And so that means, what does that mean?
All the time derivatives go away.
All the time derivatives go away. Next, it is incompressible, so rho is constant. It is horizontal. We're going to treat, so it's horizontal, so let's treat gravity as negligible. Okay, so what goes away?
Gravity terms.
Just all the gravity terms. We don't even need to think about it, whether gravity is acting in that way, direction or not, just get rid of it. Okay, steady.
Dr.
Gravity
Nickerson?
is negligible. What?
Dr. Nickerson, if rho were not constant, if it was compressible, would you have to somehow express rho as a function of x, y, and z?
So if rho is compressible, then density is a function of pressure mostly. Remember, because that's what mostly changes density is pressure. So rho would mostly be a function of, would probably be a function of pressure you would plug in. And then we have pressure as a function of r, theta, and x here. And so you could solve and find density as a function of r, theta, and x probably.
Thank you.
Mm-hmm. But yes, you would have to somehow account for how rho is changing before you were able to actually integrate and solve. Okay, all right. Now, this one is less obvious. It's laminar. And so that means flow is 1D. So we have our pipe. We have flow going on like this. And I define this direction as x. In cylindrical coordinates, usually the letter they use for that is z, but I made it be x just because I can do that. The letters you use for stuff is arbitrary. Anyway, so the laminar, so the flow is 1D. What does that mean? That means that u sub x is equal to something. And I'm going to call this v from, okay. U sub x is equal to something. We don't know what it is. What about use of r? So that's the velocity in the r direction, like this.
It's equal to 0.
0. And use of theta. So that would be the velocity at the angular direction that's coming out of our page, as you can see with my hand. What's that?
Also 0.
Also 0. Okay. This is why it's important that it's laminar. If it was turbulent, you wouldn't necessarily be able to say this. Okay. All right. And so that means let's get rid of everything that has just use of r and use of theta in it. Use of r, u sub theta, u sub r, u sub r, u sub theta. U sub theta, u sub r. All right. U sub theta, u sub r. Beautiful. Now let's do the derivatives. Dux dr is equal to, is that 0 or is it something? So what we're saying is, does this x velocity go this way change with radius r?
No.
Okay, let's think about it this way. That velocity, what is it at the wall, right there, at the wall of the pipe?
JK.
0.
Yeah, JK. U sub x here is equal to 0, and then in the middle of the pipe, it's something. So we know du sub r, u is changing with r, and by the same token, we don't know what the second derivative is either. Let's see. And then we know that, but what about du d theta?
Zero, right?
Yep, that is 0. We don't think it's changing as it goes around. And what about du dx or dz, just along the pipe?
That's the one I thought you said earlier. Is it?
Yes, that is 0, because it's fully developed. The velocity profile isn't changing. So just at any point as we go along the pipe, u doesn't change. Okay.
So we only don't know how it's changing along the velocity profile. That's what we're figuring out.
That is what we're figuring out, because that's the only place where it is changing. And all of these guys will also be 0. 0 du r dx is equal to 0. Du theta dr is equal to 0. Du theta d theta is equal to 0. The point of this is that everything is 0 except for ux, dux dr, and the second derivative of that too. Everything else on here is 0. And that just comes from it being laminar and 1D and thinking through what the velocity is and what direction it is changing in. And so what does that mean? More things. Okay, ux dur dx. Does that stay or go?
That goes.
That goes because dur dx is 0. Negative dp dr, we're going to keep it in. We don't know anything about that yet. This guy, dur dr, does it stay or go?
Stays.
It goes actually, because u sub r is 0. It's just always 0. It doesn't change. So all of these the derivatives and second derivative of u sub r and u sub theta, they also go away. This guy.
What's left?
We shall see. Du sub x d theta goes away. U sub x doesn't change with theta. Okay, now we have du sub x dr. Does that stay or go away?
Goes away.
Stay.
It stays. It stays. Yep. But du sub x d theta goes away and x goes away because u sub x does not change with theta or with x. So both of those go away, but this guy stays. So what stays? Let's see. Stays, 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 stays. That's what stays. That is very messy, but I think you get my point.
But isn't everything on the top equation equal to 0 except for that one term? So therefore that one also has to be 0?
Yes, but let's not simplify it out first. That's the conclusion, right? In fact, here we go. See? So just what you said, everything but that term equals 0, so that term does also equal 0, but let's say that's the conclusion and not in the simplification itself. And so what does it tell us that dp dr is equal to 0? What does it tell us about pressure? Pressure does not change in the
across R.
Yeah, it doesn't change across R. And what about this one?
Or theta.
Pressure doesn't change as you rotate.
Yep, pressure doesn't change as you rotate. So pressure is constant with R and with theta because dp dr is equal to 0 and dp d theta is equal to 0. So pressure is constant with R and theta. Cool. Phew. Among other things, that means that, and we'll get to that in a second. Okay, so then we have this guy right here. And so because P is constant with R and theta, which means it only depends on X, you can actually take the little partial derivative swirlies right here and just turn them into regular D's. So that's nice. Okay, so now let's write this out again, and we have 0 is equal to negative dp dx plus mu 1 over r d dr r d, and I'm just going to use v for velocity from now on for simplicity, dr, boom. It's all regular d's now because now everything just depends on one factor. The only thing that affects v is r. Here we go. We have our differential equation. dp dx is a constant here. So we can just leave it as dp dx when we integrate. We don't have to integrate with respect to x or anything like that. Right? And so now we separate and integrate. So I'm going to put dr dv dr like that is equal to, it is equal to 1 r over mu, that's okay, 1 over mu dp dx times r dr. All right, that was just some algebra. Is anyone not comfortable with the algebra I just did?
I'm gonna need a little bit of explanation.
Okay, so I wanted to get dr over on a side and then dr dv dr over on a side, so that to separate and integrate. And so I just put dr dv dr over on this side, and then I just put everything else over onto the other side. And so the first thing I did is I added dp dx over there like that. And then I want that mu over there, so that's 1 over mu. And then I want that r over there, so multiply by r. And then I want that dr over there, so multiply by dr. So I just algebraically put this dr dv dr over on this side and everything else over on the other side, and this is what I got. Okay, so this.
Question.
Mm-hmm.
So with the dx and the dr being on the same thing, do we have to do a double integral?
We do not, because dp dx is a constant. It says dp dx, but the change in dp dx, a constant pressure gradient dp dx is what we were told. And in fact, you know what? If it's more comfortable, let's say dp dx is equal to delta p over L, right? Or we could even say negative delta p loss over L, like that. Because remember, there's a pressure drop, and we usually just call that delta p L and use it as a positive number. So you could just use negative delta p L over there. We could just use that instead. In fact, let's do that. Let's just go ahead and do that. So we're going to do we want to use delta P over L or negative delta PL over L? Thoughts? Opinions?
The non-negative one.
No, does anyone care?
Delta P over L?
Yeah. No, yeah, let's just use delta P over L. I just want you to remember that this delta P, it's going to be a negative number. That's all I want you to remember. Because pressure drops along the pipe, as we know. Okay, so let's just do it like this. And so now maybe it's a bit more clear that that is a constant, which means we don't have to integrate with respect to x. Okay, so there we go. And now we can integrate both sides. Boom, boom, and boom, boom. Okay, something like 2 months ago, I think I showed y'all how to do a second order differential equation like this, where you just sort of turn this side into a d with a parentheses. So when you integrate this, it just turns into r dv dr like that. You cool with that? Because it was just d, everything inside of there. So you integrate it and it just turns into everything inside of there. Is equal to 1 over mu delta p over L times what?
1/2 r squared.
1/2 r squared plus some constant. I'm going to call it constant 1 because we're going to have to integrate again. So cool. And now we integrate again. So we got to separate out and we got to put r over on the other side where dr is going to be. We get 1 over 2 mu delta p over L r plus c1 over r. Any problems with that algebra? Oh, sorry, times dr. There we go. Again, this is separate and integrate. So I want dv on one side, dr on the other side, and I want to make sure that r is over there on the dr side or the integration will work. If there is a v, you would have to go over on the left side. Okay, we're cool though, and we can integrate, integrate, integrate. And what do we get now? Okay, let y'all do that for a second.
So we're going to have v on the left, and that's going to equal 1 over 4 mu, right? Times change in p over L r squared plus log c1 times r.
It's actually c1 log r.
C1 log r. Okay, yeah, that makes sense.
Yeah.
And then plus C2.
Plus C2. Great. That is beautiful. We're almost there. Now we just need to figure out what C1 and C2 are, and we'll be golden. And we're going to do that with boundary conditions. And we have two constants we need to find. So we need two boundary conditions. And whenever you have a second order differential equation, which this guy was, you need two boundary conditions. You're going to need two boundary conditions. So that's what we're going to do. Let's just write. So now we have V of R is equal to 1 over 4 mu delta P over L times R squared. There we go. Times R squared plus C1 natural log R plus C2. And I'm going to write out what our boundary conditions are. So we need two boundary conditions. And an obvious one is at the pipe wall, right? So at the pipe wall, what does R equal?
0.
So R is the radius.
D over 2. What is dr?
D over 2. I think I said capital R is what we were going to solve this in terms of, but it would also be D over 2, either one. And what does the velocity equal there?
0.
0. Okay, so that's going to be our first boundary condition. At R is equal to big R, V is equal to 0. And our second boundary condition, so, okay, R equals big R, that's an obvious one. R equals 0 is another one. So there's a couple different ways we could do this. What I'm gonna do, though, is I'm gonna use this boundary condition. So at R is equal to 0, you could say V is equal to V max. That would be a way of doing it. But another way would be to say dV dr is equal to 0. Right, because at the maximum, the derivative of 0.
Could you also do negative V of negative capital R equals 0? Or is
You
that...
could not, because we are in cylindrical coordinates, and so there's no such thing as negative R. It's just R is it's the same in every direction, right? So down, it's still just 0 to capital R.
Okay.
Out of the page, it's still just 0 to capital R because we're in cylindrical coordinates. So just all along the side of the wall is the same point in cylindrical coordinates. So that's not a second boundary condition. So that's what I'm gonna, but you will see why this is useful right there though. Okay, so if at R equals 0, dV dr equals 0, look at this. Look at this right there, which I'm gonna write out again. So we know that R dV dr is equal to 1 over mu delta P over L, 1 over 2 mu delta P of R squared plus C1. Okay, we plug that in. At R is equal to 0, dV dr is equal to 0, so 0 is equal to 0 plus C1. C1 is equal to 0. And actually, this kind of logically had to be true because if you look at it here, C1 natural log R, natural log of a 0 is impossible, and we know R can equal 0 here, so there just can't be a natural log of R in our final equation. Doesn't work. So therefore, we know C1 is 0. So that's good. So now let's do the other one. So now let's do V is equal to 0. Yes?
If we were working through this on a homework problem, we got to a point where we had something like plus C1 times natural log of r, could we say, hey, look, we have a natural log of r, that can't happen.
Yep.
C1 must be 0?
That's valid. Like if you know that r can be 0 in your system, which it can be, and you end up with a natural log r, you know that has to go away. That's just, it is valid to just say that. Okay, let's do the other one though. So that was one of our boundary conditions, so that gives us one of the constants. And now the other boundary condition is going to give us the other one. So now we're going to do r is equal to big R. So at r is equal to big R, v is equal to 0. So we're going to use this one now. This equation we found up here. So 0 is equal to 1 over 4 mu delta p over L times what? Big R squared, because we just plugged in big R, plus C2. So what's C2 equal?
The negative of all of that.
The negative of all of that over L R squared, like that. And then, so that just goes right there. And we end up with, going to change the colors back. Base of R is equal to 1 over 4 mu delta P over L times R squared minus 1 over 4 mu delta P over L R squared. 1 over 4 mu delta P over L R squared minus R squared. Yay! Thank you. All right, so there you go. That is how you use Navier-Stokes equation to find a velocity profile. And it is 1:52 now, I see. So class is technically over. I will post both all of these notes and the video. Do we have any questions?
Yeah, so how often in industry do we usually like find a velocity profile?
Not often, but why are we teaching you? So this is kind of, this whole last part of the class, we're kind of getting more into theoretical things, which you may not use a lot, especially if you go as an undergraduate engineer off into industry. So this is probably not a very common problem that you will encounter, but first of all, we want you to understand this because this is the basics and the fundamentals of fluid mechanics. This is what some very smart guys figured out in 1850, and all of our castles are built on it. So it's good to know for your knowledge. Second of all, as if you go on and you go to grad school and you study other things, finding the velocity profile of things could be something that you do, or you could be implementing computational fluid dynamics that uses the Navier-Stokes equation, or you could be finding shear stress for different kinds of fluids, like non-Newtonian fluids, and all of those things are built off of this theoretical foundation.
Yeah, that makes sense.
All right, cool. As per usual, I will have my office hours Zoom meeting at 2 at the usual link. And I have been recording this, so I will post it either to Learning Suite or maybe to YouTube with a link from Learning Suite. We'll see. And I will stop recording now.